remembering to use the proper function name. So W was the name of the function that related D and T in this. Sometimes people accidentally use the output variable instead of the function name. If you're trying to express this, you wouldn't want to say D of something, because D of something D isn't a function. D is like Y. It's a variable, or it's the output quantity represented with that symbol. So just make sure that if you're putting something in front of parentheses thinking function notation, make sure that that letter you're using in front is the name of a function that's been defined if you're typing something in GC, or it's the actual name of the function if it's a problem that was made up for you. So make sure you use the given name of the function if it's something that's been made up for you. Otherwise, if you get to make it up, just keep using that same letter. All right, so where we left off on Tuesday, we were talking about, we're doing some GC stuff and drawing some sunflower things, but let's see. What I want to do now that we've talked a little bit about GC, but in the realm of function notation and being able to use it efficiently, and we've talked about constant rate of change, what I want to do is kind of put all of this together and talk about constant rate of change, the relationships we talked about a week ago, while using function notation to do so, and see some of the expressions we can come up with and some of the computations we can write without doing arithmetic, just writing out function notation expressions to represent change when we know we do have constant rate of change. So not like the sunflower, that wasn't constant growth rate, that was some sort of cubic function that got steeper as it went, and the car we didn't really know anything about other than just expressions for time and distance. So if we are measuring change, so we talked about one thing, let's see, on, I think it was maybe even Tuesday last week, first day of class, talked about measuring change in a single quantity. I think we used Z's at the time just for fun. But if I want to know the change in something, the variation that happens between 2 points in time, or maybe it's the time that I'm interested in to know how much time has passed, or maybe time isn't involved at all. It's two different values of a quantity. If I want to compare them, I subtract. So we can find the change in a single quantity or the variation of a single quantity by doing final minus initial to get that change. So if it's y, I can talk about y final minus y initial gives me dy. Or if we know the amount of change, if we know the value of dy, we were talking about, I think, like phones and computers and adding and subtracting programs or apps or something. If you know the amount of change, you could also use the initial value plus the change initial value plus dy to get y final, or we can, let's see, one more algebraic rearrangement with y initial by itself, y final minus dy, the final value minus the change gets you back to the initial value. But either of these expressions are fairly common just in this order, thinking about y final minus y initial to get change, or to get a final value, start somewhere and add or subtract if it's a negative change or a decrease. This variation. So when we had two related quantities, we came up with a second set of expressions that we could use. dy equals mdx. So the variation in one quantity is a constant multiple of the variation in a second quantity. Typically we're thinking like y is an output and x is an input, but it doesn't really matter what you want to call these. I'm just using y and x for simplicity's sake. But when we do use y and x, this is the typical order that they're used in because of that independent or input sort of sense to x and the output sense to y. But the variation y, if it's a constant rate of change with respect to x, I can say that the variation of y is a multiple of, say multiple all the time of, variation in x, regardless of how much x changes, if it's a small amount, a large amount. I use the same multiple to compute the amount that y has changed. So something like, no matter, like the candy question, if I add 0.24 extra pounds of candy and it costs $2.05 a pound, then I just multiply those together to figure out how much extra I just cost myself by adding in that extra candy. Or if I drive 0.0023 extra hours at 65 miles an hour, I can find how many extra miles I drove during that time. So that sort of dy equals mdx. If you know the corresponding dy and dx values for some specific pair, you can also solve for m if you know that it's a constant rate. Like if you're trying to figure out, well, how much was gas per gallon because it cost me this much to get the regular dividing to get a unit rate sort of idea. But lots of times we know the rate and we're trying to figure out, we know how the relationship goes, but we're just trying to find that output correspondence, like how much did y change then? So if we're looking at a change in a single quantity, graphically speaking, we wouldn't have x and y axes. We just have like a number line sort of situation, just a horizontal line, and we can, whether it's y's or x's or z's or whatever variable we want to assign to the quantity that we're measuring. If I find a final and initial value, I can subtract those and find the change or the variation. Or, as I said before, if you know the initial value and the change, start at the initial, add the change, or subtract if it's a negative change, to get the final value. So if you have changes in two quantities, they're related in this constant rate of change relationship, that's when we get to use x, y axes and sorts of things. We maybe started talking about these in recitation a little bit, or have seen pictures like this in the textbook. This is something that we're going to be looking at throughout the semester, this sort of idea. If I have something, two quantities in this constant rate of change relationship, so if I'm trying to graph something that's a constant rate of change relationship, if I do that, I'm going to get a linear function of some sort. Could go up, could go down, doesn't matter where the vertical intercept is, just someplace or another. There's going to be a constant rate that relates these. So whatever this horizontal change is, visually speaking, that dx, the vertical change is going to be a constant multiple of that. So if I were to make this dx longer, dy gets larger in this case because I've got this positive rate, positive slope, using terminology from however many years ago that you started using that term. But it's the same idea. If I make dx larger, dy will get larger in this instance. If I make dx smaller, dy will get smaller in this instance. Again, if you have negative rates, that is going to impact how I use these words here. But the same idea, one's a constant multiple of the other. So let's think about the flag situation and make sure that we can do these, and then we're going to throw in some function notation. So let's say we've got a soldier lowering a flag at a constant rate of 0.75 feet per second. So let's say that x in this case represents the elapsed time in seconds since he started lowering the flag, and y is the height above the ground that the flag is, measured in feet. So we did this, I think this was a week ago, we used this example. So same example, and just x's and y's for right now. So if x is the elapsed time in seconds and y is the height above the ground in feet, if the flag began at 110 feet above the ground, we'd like to know how much it had lowered after 3.72 seconds. So think about this question for a second. I don't actually want you to compute a number answer, but just think about what it is that you would be doing to compute the answer, and symbolically in terms of y initial, y final, dx, dy, m. Like, what is it that you're doing in your computation? Does it match up with any of those? If the flag began at 110 feet above the ground, how much has it lowered after 3.72 seconds? So let me ask this. In this question, how much has it lowered after 3.72 seconds? Of these expressions, y final, y initial, dy, dx, m, which is this asking for a value of? It's asking for a value of one of those things. Yeah, the change in y. So that'd be dy. It's asking for the change in the height. Notice it's not asking what is the height. It's just asking how much has it lowered. Oh. So it's asking for a value of dy. Thinking about our relationships at the top of the page, I can find dy if I have y final and y initial, which I have y initial, I don't have y final. Or I can find dy if I know m and dx. Do we know m? Yeah, 0.75 negative, right, because it's lowering. And then dx, what's dx in this situation? Yeah, 3.72. Dx is the amount of change or variation in the x variable. X is elapsed time in seconds. So this is asking us here for, let's see if this is going to cooperate with me. I know it's going to disappear for a second, but let's see if I can get this to cooperate. So this is asking for, please work. Aha, all right. It's asking us to find dy, and we're given dx in the question, and we're given m up above, well, kind of. M is a negative 0.75. It's this, using English instead of math, so there's not a negative sign in the sentence, but lowers by 0.75 feet per second. So m is negative 0.75, dx is 3.72. So if I want to know how much the flag lowered, again, this might seem kind of like overkill, like, yeah, it's really easy to figure out, but think about carefully what quantities it is that you're comparing. So we'll run into some more tricky situations, or one where we have fewer numbers and more symbols that we need to use. So it's really important to keep in mind not just how to do the computation, but what it is that we're putting together. So, 3.72 seconds worth of negative 0.75 feet per second. That's, to do this computation, I'm going to use dy equals mdx, where m is my negative 0.75, and dx is 3.72. And if I multiply that together, I'll get negative something or another, which if I were stating it in a sentence, I probably wouldn't write the negative. I would probably say the flag lowered by whatever this comes out to be, like 3-ish feet. Meters? Feet. Don't quite know what the number is. That's not the actual important part here, but high 2 point something or low 3 point something negative number of feet that it lowered during those 3.72 seconds. So what if I wanted to know its height after 12.87 seconds? So think about maybe what computation you do, but also think about symbolically in terms of these dy's, dx's, y final, y initial, what is it that we're doing? So what variable or what expression are we trying to find a value for according to this question? Yeah, y final. We want to know its height at the end, not how much the height changed, but what is the height at the end. So we're trying to find y final. Let's put yf. So we'd need to know y initial and dy to do that. Well, this isn't either of those. What is this 12.87 seconds? That's dx. 12.87 seconds have gone by, like 12.87 minus 0. So this is dx. If I want to find y final using dx, it's kind of a combination of these things up here, right? I can find the final height by knowing where it started and then how much it changed by, but to find how much it changed by, composition of functions, I need to know the rate at which it was changing and how long it was changing at that rate. So, like, if you're looking at this problem, this probably seems like it's not a very hard arithmetic question. It's annoying numbers with weird decimals, but it's like, oh, well, it was at 110 feet, and then it went down for 12.87 seconds at that rate. But that y final, all that is we take the initial height, and then we add, well, it turns out to be subtract, the change, which instead of using dy, we have to calculate dy. So we'd have the y initial plus this negative number that comes as a result of our descent rate times the amount of time it was descending at that rate. So symbols, this is what we're doing, y initial plus m dx. M happens to be negative. But the final height, you might have been able to maybe get this easily without thinking about the symbols, but I want you to concentrate on how these are related, because in every constant rate of change situation, we're going to have these same relationships. And despite the fact that not everything in life changes at a constant rate, there are a heck of a lot of things that if you look at a small period of time, just like, I'll call it a moment, the term your book uses for a small amount of time, or a small amount of whatever is changing in the independent variable way, it's close enough to constant that we can assume that. Or if we make the moment, the increment of independent variable dx incredibly small, then within a small moment, we're going to have essentially constant rate of change. So it's close enough, and we could make it closer if we want to, if we need to for some reason, like error computation-wise. But in terms of the computations for this, we just say, oh, well, it was at 110 feet, and then it went down by 0.75 feet per second for 12.87 seconds. But this general expression here, this could be used not just in this situation for this find the height after 12.87 seconds. What if I asked you to find the height after any number of seconds labeled like x seconds? Oh, well, if it was after x seconds, we do 110 minus 0.75 times x. Or maybe I know its height at a specific weird point in time, not at the beginning, but I want to know its height a little bit later than that. I can still use my rate to work from any known initial value of y, height, to find a final value of y, whether it's initial as in time 0 or initial as in just any initial value that I happen to know about. So let me clear this off for just a second. So if I want to describe the flag's height after any x seconds, that's, well, what I just did a second ago. It's height y after any number of seconds x, based on, still this is question 1, so still based on this premise of starting at 110 feet, 110 minus 0.75 times x, the number of seconds that have elapsed. 110 minus 0.75 feet for every second, or for any number of seconds. It doesn't have to be whole numbers of seconds. It can be any increment of time as long as we measure it in seconds, multiply by negative 0.75 and add that to 110, or multiply by 0.75 and subtract it from 110, the starting height. So here's the slightly more complex situation then. So still a flag ceremony, trying to lower this flag. Suppose the wind was whipping the flag around, it got a little tangled at first, so time 0, nothing constant rate of change was happening. The constant rate didn't happen until after I was able to get it untangled, which was 20 seconds after starting. It took a little bit to untangle everything. But after that 20 seconds had passed, the flag was descending at its normal flag ceremony rate of 0.75 feet per second. And let me move this guy if I can. Oh, come on. Don't do this. Well, what do you do with that? No. If the flag was at 104 feet above the ground at time 20, figure out how much it would descend in the next 3.72 seconds. Is that any different from the part A question on the previous slide? No. Doesn't matter what height it is or what time it is. If we're talking about how far the flag would descend during 3.72 seconds, if it's descending at a constant rate, it's the same amount. It's that 3.72 times 0.75 downward, or negative 0.75 times 3.72 is that dy value, right? So just like in on the previous slide, we didn't use the initial height to answer that part A question. How far does it descend, or how much does it lower during 3.72 seconds? If it's changing at a constant rate, that initial y value, that initial height, doesn't play into it. That's good to know, but it doesn't help us do the computation. So this part B question, there wasn't one like this on the previous slide. What would the flag's height be by this time? That is at 23.72 seconds into the ceremony. Huh? Is this question B asking us for a value of dy, dx, y initial, y final, or m? Y final. It's asking us for a value of the height after something's happened. All right, so it's asking us for this y final. So same relationships as before. They're no longer at the top of the screen. But to find y final, if I know the starting height and I know the rate at which it's descending and how long it's doing that for, I should be able to get my new height by, well, subtracting is what it turns out to be. It's just that it's not the 110 feet from last time. It's 104 feet minus 3.72 times 0.75, right? So 104 feet plus dy. dy is mdx. Part A is just the mdx, 3.72 times negative 0.75. Part B is y initial plus mdx, 104 in this case, plus negative 0.75 times 3.72. Y initial changed from the last question, but the m is the same, and the dx is the same dx we had from part A. But just keep in mind what the meaning of these quantities that are described. Is this a change or a variation in something that's being asked for or given? Or is this an actual individual value of x or y, of time or of height, or is it the rate? The rate's the easiest one to pick out usually. Completely different sorts of units, and it's not something that we have to think about changing. All right, so think about this one. What would the flag's height at 45.31 seconds into this ceremony be? This one where it was tangled for a while at the beginning. Think about how you would do that computation, and think about what symbols the things you're doing are assigned to. Attempt to get this guy back again. Nope. And there's a part D if you want it. We'll go through both C and D. I'm just going to have to get this out of presentation mode to be able to write again, being stubborn. So the part D described the flag's height at time x seconds into the ceremony for any time x past this tangled. I just stopped it at 100 so the flag isn't going out on the ground. So. All right, so let me do this. Make this a little bit bigger, maybe. It's the best it's going to do for me. All right, so this part C here. Why is it being stubborn? Hold on a sec. The screen is so small that I can't start and stop things. Ugh. All right. I don't know why this is being stubborn. I apologize. All desktops. Well, I guess we'll forget that then. We'll work on this another day. I don't want to waste your time with technology issues today. So I'll write it on the board old-fashioned style if I can get this to there we go. All right, that's coming up next. But, so the flag's hide at 45.31 seconds into the ceremony. If I wanted to figure this out, I need to know, well, how much time has the flag been being lowered by this point in time? What question is that? How much time has the flag been being lowered at this constant rate? It's not 45.31 seconds. We have to subtract 20, right? So figure out how much it is past 20. That's an x final minus x initial in reality question. So x final, 45.31, x initial, the time it started dropping at this constant rate, or being lowered at this constant rate. So 25.31, easy enough to maybe do mentally since 20 is a nice round number. But let's see, I was hoping maybe I could get this to right anyway. Not today, apparently. All right, so 25.31 seconds at 0.75 feet per second lowering rate, negative 0.75. And then we want to know what's the height. So that's a y final. So I need y initial and then minus that amount. So we've got a y final is y initial plus, although it ends up being negative, dy, y initial. We end up having this, well, plus or minus, whatever you want to, however you want to mentally think about where's the negative. Is it in the situation or is it in the m value? It's up to you. Kind of if you're talking out loud, it might come out one way. But our initial height, and then minus 0.75 times the amount of time that's passed. So our initial height of 104, and then minus 0.75 times 25.31. 0.31? 0.72. I don't know where 0.31 was from. Something else. Oh. It was 0.31. Sorry. Looking at the wrong part of the question. There we go. 25.31 seconds have passed between time 20 and time 45.31. So 25.31 seconds at this negative 0.75 feet per second would mean that it lowered by that product number of feet, putting its new height at 104 minus that amount that it lowered by. So if I want to describe this at any time x seconds into the ceremony after time 20, all I'd have to know is, well, how far is x past 20? Just like I needed to know how far is 45.31 past 20, this time when the constant rate started going into effect. So all I have to do is, instead of saying, oh, for dx, it's not 45.31 minus 20, it's x minus 20, whatever x is, and that's our expression. That's the whole thing. So if this isn't a specific time, if it's an x time, the dx we used here was 45.31 minus 20. If we just change that from x, that's the expression we need here. So just minus 0.75 times x minus 20. And there we go. Don't have to do any other computation. You don't have to multiply that out. You just write it like that. In this format, which if you're thinking about writing linear equation sorts of things, this is related to point slope form that you may or may not usually like to write equations into, but it's very helpful. It involves not having to compute things. You can just write down the information that you know. So the new height at any time after 20 seconds, x seconds, something where x is larger than 20, I'd do this expression to find its new height, its final height, its height after those x seconds have passed. As long as x is past 20 seconds when it's dropping at a constant rate. If x is less than 20 seconds into the ceremony, we don't know anything about this. So this would only apply domain-wise to x values 20 or larger. All right, so let me see if I want to do this. I'm just going to open this up someplace else so that I can write on it, potentially. All right. Still don't know why this is showing up as a little miniature doodad here. But, yeah, unfortunately, I keep doing that, and it keeps doing the same thing. And it's not showing up with the little dot here, so I think it's like running on some other desktop and not wanting me to run it. We'll see. That makes it go like that. So, yeah, it's a mystery of today. But, so, if you looked at Canvas, I put another document on there today. Let me just open this up real quick. I put another document available for you to look at. There's lots of them on there. It says car and sync. So the car was the function notation stuff we did last time. The sync is something I want to show you now. So I just combined them into a document, but just thinking about constant rate of change in a couple of different examples. So with constant rate of change and function notation all together, let me make this bigger. This is the stuff that we talked about last time, this first page of this, and I'll make this larger. Let's see. Okay. I don't know why I have to infer reading order, but. All right, so the distance traveled by the car between 2 and 5 seconds, a second, 4-second interval, and all these expressions before. So I just kind of put those on this document so you can see those. Now, the second page here of the same document is some other things related to kind of a combination of what we did with car and function notation and what we were just talking about with the flag and doing this using the whole idea of dy equals mdx, including sometimes calculate dx, sometimes be given dx. How do you find all these different things? So you can pull up your own copy of this to have it in a maybe more appropriate size to see. Let's make this a little bit bigger. But suppose that we have h equals w of t. So w is our function name again. T is time in minutes after pulling a drain plug, and h is the height of the water in a semi-clogged sink. It's measured in centimeters, so it's dropping at a constant rate, but it's not very quick. So it's just slowly the water's going down. Get some Drano or something. So it says in here, assume that the water's draining so that its height decreases at a constant rate of 1.23 centimeters per minute. So I'll put up a few questions here. But question 1, A and B, kind of go together. That's why they're 1A and B. Part A, write one computation and one expression using function notation for the change in the height of the water in the sink between time 2 and 6 minutes. So thinking about what we were just doing with dy and mdx, that sort of thing. So write out the computation you do, write in symbols what it is you're doing, but realize this time instead of necessarily having just dy's and dx's and that sort of thing, we have a function w, so we can refer to things by using function notation also. So think about the change of the height of the water in the sink between time 2 and time 6 minutes, how you calculate that, and how you could express that in using function notation. There's maybe a couple different ways too. So since we have function notation, or a function name, we have more options as well, beyond what we did last time. And then there's additional questions. I'll leave it at this, but if you want to scroll through this document, this is what's on Canvas. It's in that module 1. But if you want to work ahead, but think about these values and the symbols that can represent them in a couple of different ways. And then 1B says, suppose that W of 2 equals 8. Write a computation for W of 6. difference between this and the car thing that we did before. The car, we didn't know anything about constant rate of change. This one we do. So that's why there's more ways we can write this. Around with this one more time. All right, so for this question 1A, computation you could do, what computation could you do that would tell the change in the height of the water between time 2 and 6 minutes? Let's see, the change in the height of the water is asking for a value of, in general, dy. I don't have it there. The change in the height is the output. So not thinking function notation, just what we were doing last time. Oh, I need a dy. I don't know the initial and final height. I could express those with function notation. And so I could do that. Or I know that it's 4 minutes gone by, constant rate of 1.23 centimeters per minute. So in terms of how I could express this, well, 4 minutes, but that comes from 6 minus 2, dx multiplied by m, our constant rate at which the water's height is decreasing. So I'll use a negative 1.23. But just negative 1.23 times 4 would be a computation we could write. Now, if I wanted to write an expression with the symbols we were just using, that's m dx, right? Since we have a function with function notation also, I could refer to these also as, oh, well, to get, this is m dx, otherwise known as dy. Our goal for part A is find a value of dy, find a value for the change in the dependent quantity, change in the height of the sink. But since I have function notation here, I could refer to just, oh, y final minus y initial, they have names, even though I don't know what they are. I can say, oh, well, it's w of 6 minus w of 2. So y final minus y initial. Since those have symbols I can express them with, I can write it without knowing the value of either one. But w of 6 minus w of 2, this is supposed to be capital W like that, but W's all kind of look the same out of context. So there's a couple different ways we could write it. This is a computation, or negative 1.23 times 4. I could call it m dx, y final minus y initial, or specifically with the numbers from this problem, that's w of 6 minus w of 2 also. So if I know that w of 2 is 8, w of 2, that would be the height of the water at time 2, or the beginning of the situation described in part A. Write a computation for w of 6. That would be the height of the water at the end of part A. So if I know y initial, write a computation for y final. So if you can read a question and kind of translate it in terms of those, they all turn out to be the same combination of operations. It's just making sure you understand what the given pieces are. So, if I know y initial and I know dy, I can find y final, right? Y final height is going to be my initial height plus the change, or plus mdx if I want. And all this said is, suppose that w of 2 equals 8. Oh, well, w of 2 would be this, the initial height, and we just calculated the change during that 4-second period last time. Well, I don't want to write it this way, because that'd be like the identity statement. W of 6, the height at the end, is equal to w of 2 plus w of 6 minus w of 2. Well, yes, it is. So we'll write it the other way. You write it, w of 2 plus negative 1.23 times 4, or times 6 minus 2, y initial plus mdx. So this computation, if I know that w of 2 is 8, initial height of the water minus 1.23 times 4. So it started at 8 centimeters worth of water in the sink, went down by 1.23 centimeters per minute for the next 4 minutes. Now I know the height at time 6. So you can maybe think your way into the answer, but make sure you also realize that it's not a different problem every time. It's still the same set of relationships that we've worked on in previous questions. So this w of 6, y final, is y initial plus mdx, or y initial plus dy, the change in y. So we can write a computation. This actually, knowing that value of 8, means we know numbers for all of the pieces that we need to actually do a computation with. All right, so again, this height, the rate at which the water is dropping for the whole problem is this 1.23 centimeters per minute. So take a look at 2a and b. This is just slightly more general. Write a computation and an expression with function notation to represent the variation in the height of the water during an interval of k minutes that start at time t equals 4. So that is, during the time interval 4 through 4 plus k, what happens to the height of the water? And then for part B, suppose that w of 4 is 5.7. Write an expression for the water's height after the next k minutes have passed. I really would like this to work. So for 2a, this is asking for a value of the variation in the height, just the dy, dh if you want to talk about it like that, during the interval 4 through 4 plus k. So obviously, since there's a mystery k, I'm not going to be able to come up with a number for this. But since the height is dropping at a rate of 1.23 centimeters per minute, instead of having 4 seconds to go by, or 4 minutes to go by, I've got k minutes to go by. Oh, so change by 1.23 times k in a negative direction. So decrease by, depending on what k is, this much during that k minute interval rather. 4 plus k minus 4 is k. So that's why it's k seconds that have gone by. So if I wanted to write an expression using function notation for how much the height had changed, instead of just this mdx, we can write the y final minus y initial, just like before, only instead of w of 6 and w of 2 or whatever it was, we have w of the final time, 4 plus k, minus w of initial time, 4. So this is pretty similar to the expression you did in your quiz at the start of class today. That one didn't have anything to do with any constant rates of travel, just finding the distance traveled during that time interval. This is the amount that the height of the water in the sink would have decreased by. So I know this is going to be some sort of negative. It's negative 1.23 times whatever k is, because it's changing at a constant rate, because the water is draining at a rate of 1.23 centimeters per minute. This gives me the amount that it drains by, but so does just comparing the beginning and the end. If you don't have a constant rate of change, you can always write this sort of expression with function notation if you have a function. If there isn't a constant rate, you can't just decide that there is one and make one up. But if you do have one, you have multiple ways to write these things. So again, for part 2b, suppose that w of 4, y initial, is 5.7. So the height of the water in the sink at time 4 is 5.7 centimeters above the bottom of the sink. So write an expression for the water's height after the next k minutes. Here's how much it changes by during that next k minutes. So if I know the starting height, 5.7, I'm just going to tack that on. 5.7 minus 1.23k. So y initial minus m dx. This is the dx, y initial, either plus a negative or minus, depending on how you want to say the sentence in your head, but it ends up being a subtraction from 5.7, regardless of if you call it plus a negative or subtracting a positive. But again, in any case, write an expression for the water's height after the k minutes have passed. Well, in other words, it's looking for what is w of 4 plus k. It's the height at 4 plus what happened during the next k minutes, which happens to be a negative something that happened. And then the last question on here, the most general of them, write an expression with function notation for the variation in the height for dy during any general interval starting at time 5, meaning 5 through mystery t. So t was the name of the time variable, so 5 through whenever, I'll just call it t in general. So we don't know one length for the interval, but we can express it using t, which is a variable. So think about how you would express the amount of change in the height of the water. There's obviously going to be limitations on how big t can be before the water's actually all finally drained out of your clogged sink. Don't worry about the domain, just the expression in general. And then 3b, again, now let's calculate the final value of the height. Find the value of the height at some mystery time lowercase h. Write an expression for the water's height at the end of that general interval, or in other words, at time t, which is sometime after time 5, apparently. But the key to all of this is these relationships, and you can use function notation to express any pieces of that, like y initial or y final that you want, if you don't have a specific symbol value or number value given. copy it anyway. There. Can't write it, I can type it. All right, so if I want to talk about the general change in height of the water during an interval from 5 to t, if I want to use function notation, then that's y final minus y initial. I can do this sort of thing. Between time 5, the beginning, and time t, or over the interval 5 through t, I can think of W of, oops, it was capital W, y final minus y initial. And I can do it that way. If I wanted to use less function notation, if I want to just express this another way, the variation in the height of the water during this interval, I'd need to know how much x, or t, changed by, and the rate, so mdx. So I could do this negative 1.23 centimeters per minute for how many minutes? T minus 5 minutes, right? However much larger t is than 5, that tells me the length of this time interval. So either y final minus y initial or mdx. Those both give me the same thing. They both give me dy, the change in the height, variation in the height. So if I suppose that the height at time 5 is some general value h, and I want to express the water's height at the end, W of t, but I know the height at the beginning, W of 5, thinking about, oh, well, this is just assigning values to this, so this W of 5 is h, so I can call this h. And I want to write an expression for W of t. Well, I know the height at the beginning. I'd like to know the height at the end. No, as in I have an expression for it. But if I want to know y final, ooh, let me go back from here so I'm not typing in huge letters. I guess I will change it manually. I'll just do this kind of quickly. Y final is y initial plus mdx. So if I'm thinking of what we just had above, oh, y final is what I want, the height at the end of the general interval, W capital. My initial height is W of 5, otherwise known as h, and mdx was this negative 1.23 times t minus 5. So this is my starting height, and then what happened afterward. So it started at height h at this time 5, and then it decreased at a rate of 1.23 centimeters per minute for this many minutes. This is a linear function if h is a parameter here. So W of 5 is h. W of 5 is one specific height. So this use of h is using h as a parameter here. I could say h is 17, I could say h is 4.9, I could say h is a lot of different things. It's going to be one value. It's just the height at time 5. And then the height of the water, W of t, decreased after that. So y initial plus mdx with these more general sort of values or parameters thrown in there makes this look like a linear function. So at any time t, this would give an expression for the height of the water. The h wouldn't change, but I could make it a different h for a different situation. The height at time 5 was a single number. But for all these different values of t, anything after time 5 that I want to pick, this would work. And in fact, even before time 5, this would work. If I picked a number that's less than 5 in this situation, it's not nonsense, unlike the flag question. picking a time less than 5, since the water was dropping at this constant rate all along, not just after 5, would just happen to give me values for the height that are more than whatever lowercase h is. All right, so in any case, these questions, you'll see all of these posted in this module 1, this third thing down, the car in sync with function notation, as well as the car questions that we went through the other day. It's just so they're all kind of in one place, all this practice with function notation, and in the case of the sync stuff, constant rate of change as well, and inserting some function notation into that. So where we're going with this is, as I said, constant rate of change seems like it's kind of limiting, because like, oh, well, not everything changes at a constant rate. I don't drive on the road at a constant speed for more than, a little bit at a time before something happens. But if you only look at small increments of time at a time, you can piece them together over each small increment. You can imagine a constant rate if you pick small enough moments, small enough increments of time. And within those small moments, like maybe within any 1 second driving down the road, your speed isn't going to change that much. So you can, like, from 1 second to the next, you might want to readjust because you actually were accelerating, or maybe to be more accurate, maybe pick a tenth of a second. Over a tenth of a second, your speed isn't going to change that much from the beginning to the end of that tenth of a second. So you can use your speed as if it were constant for that tenth of a second. You're just going to need to recalculate for the next tenth, and recalculate for the next tenth, and so on and so on and so on for how long you want to go, which is a lot of tenths of seconds if you're on a long drive. Just like it's a lot of like silver ants going across the country. Like there's some large numbers, large amounts of really small things put together though can cover any amount that you need. It's just how much patience do you have? Now, in terms of doing these sorts of estimations or assuming constant rates over small intervals, if you were doing something like that manually, it would be extremely exasperating. Since we have computers, they're very good at doing that sort of tedious stuff that people find repetitive and boring and like, oh my gosh, I'm never going to finish this. I'm doing the same thing over and over. Find this value, estimate that, subtract, divide, add it on. Over and over and over again. Computers can deal with that well. And once we've looked at some of the patterns that arise, we'll find some algebraic shortcuts so that you can do it in an efficient amount of time also. But just the build-up to this is, in many, many, many situations, not every situation under the sun, but in many situations, if you look at a relationship between two quantities, if you look at only small amounts at a time, like think of zooming in on a graph, it'll look essentially like a straight line. The things that are exceptions to this are things where there's a sharp corner, like think absolute value graph, something where it's got a corner. No matter how close you zoom into a corner, there's going to be a corner, which would make it not look like a straight line. So this whole straight line idea is the idea of finding a slope, and slopes in linear functions represent that constant rate of change, that ratio of vertical to horizontal, dy to dx. Since we can look at small amounts at a time, many, many, many situations, even though they're not constant rate of change all the time, one constant rate for everything, each little moment or increment we can think of as having its own constant rate and use the math of constant rates of change and the functions that go with it to express what we need. Just it ends up being a sum of a whole bunch of little mdx with one rate for a little bit of dx, and then a second rate for another dx, and a third rate for another dx, and so on and so on and so on. So we can add them all together. We're going to have huge sums of things that tell us how much change was accomplished because of rates that were actually varying, but within small moments at a time were essentially constant. So we can get good estimates, just numerically speaking, and we'll also talk about how we can actually get exact values. And we're going to deal with this both using GC and getting it to do all these ugly approximations for us, but also we'll kind of look at the overall process and we'll come up with algebraic ways to cut through all the repetitiveness and express things just using new formulas. So in any case, constant rate of change is the key to everything that we're going to be doing this semester, even though we're not just going to be looking at things that change at one rate all the time. So I'm going to take a look at let's see, I forget what section numbers it is. I'm going to list some section numbers for you to read in your textbook over the weekend, but it involves looking at constant rate of change in small moments. So to prepare for what we're doing next week, keep in mind, there's one other thing. I mentioned this on Tuesday, but I said I'd remind you again today. There is a quiz that's going to open up at 3 p.m. this afternoon and be open through midnight. It's more than one question and 1 point. It counts into your regular quiz. It's in iMath. So if you log in here, you won't see it just yet, but I can see it. The things that are grayed out on here when I pull up mine are things that I can see that you can't quite see. It will show up at 3 p.m. as something that's due, and it's going to be due tonight. It's just a few questions, and it's about things that we've talked about, not just brand new stuff, not things that are going on next week, but think about functions, think about constant rate of change, and the things that we focused on so far. So it's a fairly short quiz. I would guess if you're focused and looking at it, it'll take you 10 minutes or less, but don't try to start this at like 11:55 tonight and hope that everything goes well. It's not timed, but unlike homework in iMath, you can't try it over and over again until you get it right. Even for reduced credit, you get one try, you submit it, and it'll tell you whether you're right or not after the deadline's passed. So you will find that out. If you want to stay up till midnight, you can see your score on it. Otherwise, just find it tomorrow morning. But that quiz is due, and you've also got a homework that's due on Saturday night. So the colors on here, by the way, are kind of like stoplight colors. If there's something red, it's almost due. The due date's approaching soon. Orange and yellow are a little farther off. If you see something in green, it's a don't worry about it. Just keep going. You can get to it later. So, in any case, I will see you next Tuesday, if not before. This is so frustrating.